In this video, we will summarize the convergence traits of power series, which is a theorem in our textbook in 11.8, I believe. But basically, the theorem says, given a power series centered at A or centered elsewhere, and all the examples, well, actually, these last two examples we looked at were centered at 0, but this one was centered at 1. Again, doesn't really matter at the end of the day. But basically, there's three possibilities for convergence of a power series. Case number one, the series converges for all x. Much like the Bessel function, when we solve our limit via the ratio test, if we get conclusively that it's 0 or less than 1 regardless of x, then it can converge for all x. And all that means is that this function, such as the Bessel function j0 of x, you can plug in any x you want. And it's essentially the domain of this function is all real numbers. There are no problem areas. Anything is valid. Which is good. It means you can do whatever you want with it. The second case is the series converges only when x minus the center of the series is less than r, the radius of convergence, and diverges otherwise, much like we saw in this second example. It converged between 0 and 2, and it diverged past 2, to the right of 2 and to the left of 0. R is what we call the radius of convergence, as we've talked about. The interval of convergence is the inequality itself. And the another thing that's very important not to overlook in those cases is the convergence at A itself, at the boundary point, both plus and minus A, is indeterminate, meaning that because the ratio test, is not conclusive at those boundary points, means we have to consider those separately using another convergence test. And then the third possibility is the series diverges for all x, except for specifically at the center itself, or the value, which again, as I was saying, at the center, at specifically at 0, it's kind of silly. And basically, in case 3, the power series is basically useless. Whereas in case 1 and 2, they still have an interval of convergence. There's still convergence for particular values of x. Which again, they're still useful in those cases. And sort of summarizing a lot of our examples, a geometric series is a good example of a power series where it has a finite interval of convergence. Well, there's an infinite number of numbers in there, but it's not all real numbers. It only converges from -1 to 1, not including either of the boundary points with a small radius. We looked at this example, which only converges at 0, and you could say technically there is no interval, or you could just say it's the set of numbers 1 itself with a radius of 0. With example C number 2, so example C were these two that we did here. With this one, we solved that it had a radius of convergence of 1. So this table, I put it in our notes just to sort of collect all the information, right? Because we've done a lot of math, looked at a lot of examples. And I just wanted to sort of go back over this theorem from the book and show you, it's not, I've made it sound very complicated in the last few videos, but basically there's only 3 possibilities, and you always can use the ratio test to figure this stuff out. And it converged specifically from 0 to 2, non-inclusive. Again, this is the hardest thing to solve because you actually have to do the math, you have to find the interval by the ratio test, and you have to check the borderline cases. But the radius is always pretty easy to figure out, as is the interval. Again, there's a bit of math involved. And again, this is a typo. This should be starting at 1, not 0. And then we had the Bessel function of order 0, which we figured out that x converged for all real. Basically, it does not matter what x is, that converge for all values, x in the reals. Or another way you could write that is, we could write that the radius is equal to infinity, which is a little bit of a strange thing to write because, again, nothing can be equal to infinity. But basically, by writing that, what we kind of mean is it converges everywhere. Or again, we could write that as an interval of numbers from -infinity to infinity. But again, that's kind of useful because that just means the domain of the Bessel function was all reals. And there's an example here. Go ahead and try it yourself. So as usual, there's an example of a power series. Try it on your own. See if you can figure out which of the 3 cases this example falls into. And go ahead and try to solve the interval of convergence. We can come back in lab or in class and discuss it. Now we will go through, there's one last video for today's online lecture, which is representing functions using a power series. So this is kind of the last idea before lab, and it's a pretty cool idea. Get into this in the next video.